Hello everyone. So today we're going to continue talking about polynomial functions, and specifically we're going to look at polynomial functions of degree 2. So they're going to have an x squared in them somewhere. Okay? Now this is a type of function that you would have looked at either in Math 20-1 or 20-2. They are also called quadratic functions. And these are very common. If you think in everyday life about even like someone throwing a ball or kicking a soccer ball or something like that, it follows kind of this path, right? And this is what they look like graphically. This is called a parabola. Sometimes they face upward like that. Okay, and so there's lots and lots and lots of applications of these types of functions. So we're just going to start out by doing some investigations and looking at 3 different functions and putting that out on this graph over here. So we've got these 3 functions, f of x, g of x, and h of x. And I'm going to graph those using a calculator. So here we go. Okay. Y equals. So I'm going to clear anything out that was in there. And the first function is y equals x squared. Second function is y equals negative x squared minus 3x plus 4. And then the third function is negative in brackets x minus 2. Whoops. I pressed the wrong button there. Okay, hold on. X minus 2, bracket squared, and then minus 4. And one thing that you'll notice about this form is that we kind of have this binomial squared and then minus a number. This is actually called vertex form, and it tells us something about the graph. So that's not really a requirement of this course, but it is something that you've seen before, so I just want to remind you of that. Okay, now I'm going to go to my zoom button and hit number 6 for standard, and there are my 3 functions. Okay, so the first one was y equals x squared. That's the blue one. I'm just going to sketch that in here, and I'll just stick to the same colors. Okay, so this is f of x. And then we've got y equals negative x squared minus 3x plus 4. And that was the red one. So that's this guy over here. So I'm going to graph that as well in red. And that is g of x. And then finally we've got h of x, and that was the black one. And that one looked like this. This is down here. Okay, and the y-intercept 1, 2, 3, 4, 5, 6, 7, 8 was negative 8. Okay, so that's sort of down here. And this was h of x. Okay, so this is visually what these 3 functions look like. You can see they kind of have the same shape, but a couple of them face downwards, a couple of them open upwards, and then of course this point over here, this is a maximum, this is a minimum, or sorry, this is also a maximum, and then on the blue one it's a minimum. That's called the vertex. So the vertex has been moved around as well. Okay? All right, now let's look at these one at a time and do the same sort of analysis that we did yesterday. Okay, so if we're looking at y equals x squared, that's the blue graph. In this case, constant term is actually 0 because we're not adding or subtracting any number to it. So this is just 0. You can think of this as plus 0. Okay, sign of the leading coefficient. So the leading coefficient in this case is the coefficient of x squared, and it's 1x squared. So the coefficient is 1, which means it's positive. Okay, if we look at the end behavior of the blue graph, it starts in quadrant 2 and ends in quadrant 1. Okay, so our end behavior is quadrant 2 to quadrant 1. Okay, the domain. So if we look at arrows here, this arrow over here is going up and left. So if we're specifically thinking about domain, we want to think about horizontal directions left and right, and then this one goes right. So if I got an arrow going left and an arrow going right, my domain is that x is an element of the real numbers. Okay, range, if I look at my arrows, both of the arrows are going up. There's no arrow going down in this case. So there's got to be a lowest value, and that happens right here at 0. So the lowest y value is 0, and then it goes up from there. That means that y must be greater than or equal to 0. Okay? All right, let's talk about g of x. That's the red graph. Okay, so g of x, the constant term in this case is the 4, plus 4. The sign of the leading coefficient, so we have negative x squared. That's like negative 1x squared. Negative 1 is the leading coefficient, and so its sign is negative. If we look at the end behavior for the red graph, that starts in quadrant 3 and ends in quadrant 4. So this is Q3 to Q4. Okay, domain. If I look at this arrow over here, that one horizontally points left, and this one points right. So my domain is that x is an element of the real numbers. And then if I look at my range, okay, if I look at my range, I have arrows going down, but I don't have any arrows going up. So there's got to be a highest value, and that happens at this max point here. Now we can't see clearly on the graph where that is. So what we're going to do is take out that calculator, and I'm going to use my maximum function, which is under that calc menu. So you got to hit second trace, and then I'm going to hit number 4. Okay, and if the cursor is on the wrong function, just use the up or down arrows and it'll move it until, okay, now it's on the right one because it's red. Okay, now here's my max point right here. So I need to go a little bit to the left, which is over here, and a little bit to the right, which is over here. So I'm going to go left bound is like there, and right bound is there. And that point is negative, basically negative 1.5, 6.25. Okay, so this is negative 1.5, 6.25. And essentially what that means is that the highest y value is 6.25. And so my y values start at 6.25 and then go down. They get less than that. So y is going to be less than or equal to 6.25. Okay? Finally, for h of x, okay, so constant term. So here's the thing, a lot of people think the constant term is negative 4, but in fact, the constant term is the number once the polynomial has been expanded. So this is not in expanded form yet. So to figure out the constant, we actually need to multiply this out. Actually, I'll switch colors. Okay, so we're going to get h of x equals negative x minus 2 squared minus 4. Now, if I square that entire bracket, that is actually negative x minus 2 times x minus 2 minus 4. Okay, and now I have to expand out the multiplication of these two binomials. So negative x times x is x squared, And then x times negative 2 is minus 2x. And then I'm going to move on. Negative 2 times x is minus another 2x. And negative 2 times negative 2 is plus 4. Minus 4. Okay? And I can simplify that a little bit because there's x terms that are like. So negative 2x minus 2x is minus 4x plus 4 minus 4. And then I can distribute the negative sign in. So this is going to become negative x squared plus 4x minus 4 minus 4. And so all together, negative x squared plus 4x, and then negative 4 minus 4 is minus 8. So this is the expanded version of this function. And what that actually means is that my constant term is negative 8. Okay, so really important for constant term, make sure the polynomial has been expanded. Okay. This format, as I said, it's called Vertex Form, and it actually gives us information about this point here. So it is useful, but it does not tell us about the constant. So we do need to expand that to get that value. Okay. And that happens to be this over here. This one, by the way, is 0, and this y-intercept over here is 4. So foreshadowing, looks like there's a connection between the constant of each function and the y-intercept. Okay, so sign of leading coefficient. Let's move on. For h of x in expanded form, it's negative x squared plus 4x minus 8. So leading coefficient is negative 1, so this is negative. The end behavior, like the previous function, also goes from Q3 to Q4. Okay. Domain and range, again, we have arrows left and right, so x is an element of the real numbers. And then for the range, we have this highest point over here. So again, I will use my calculator to figure out what that is. Or if you remember what vertex form is, you might remember that it's actually the point 2, negative 4, but you don't need to know that. Second trace, maximum is 4. So I'm going to go to this guy. Let's see, where is it? There it is. Okay, so that's the left. Enter. Move it over to the right. Enter, enter. And you can see that that point is 2, negative 4. So I'll put that in our notes. What that means is that the highest value of the function is negative 4, and then it goes down from there. So y is going to be less than or equal to negative 4. Okay, now if we're going to make some generalizations here, we already sort of talked about what the constant means, and this is actually exactly the same as for linear functions. The constant in the linear function was also the y-intercept of that function, and that's true here as well. So the constant in the equation equals the y-intercept. Okay, remember though that constant you have to expand to be able to see where the constant is. The sign of the leading coefficient well, again, similarly to linear functions, this is going to affect the end behavior. When it was positive, the end behavior was Q2 to Q1. When it was negative, it was Q3 to Q4. So this affects end behavior. Okay, so positive Q2 to Q1. Negative Q3 to Q4. Okay? The domain and range. So as you can see, x is just any real number for all three of these functions. So in general, unless there's a context where we have to restrict it, the domain is x is an element of the reals. The range is restricted because there's going to be a max or a min value. So if there's a maximum y value, the range will be less than that. So y will either be less than or equal to a max value, and that's the case when it sort of opens down, or y will be greater than or equal to a minimum value. Okay, and that's basically true for all of these quadratic functions. Okay. Let's talk about factored form, because what we're really looking at in this first scenario was we looked at this standard form, and actually I should have mentioned this at the beginning, but this is the standard form, f of x equals ax squared plus bx plus c, where everything has been multiplied out, okay? A cannot equal 0 here, because if a was 0, there'd be no x squared term, and then it wouldn't be quadratic, okay? But this is standard form where everything is expanded out. We can sometimes also look at factored form of a quadratic equation if a particular function factors. And in this course, you're not really responsible for factoring quadratics. If it's factored, it will be factored for you. That is going to give you some different information about the function. Okay? So let's say, for example, I take something like this. Oh, whoops. Y equals x squared minus 7x plus 10. Okay? Now, it just so happens that this factors, and again, if you know how to do this, great. If you don't, this is not part of this course. This factors into x minus 5 times x minus 2. Okay, and if you wanted to check that, you could expand it out and see that they are equivalent. Now, this is the standard form, and this is factored. Okay, standard form gives us information about what the graph's going to look like. And again, we can look at the leading coefficient, it's positive, so we know the end behavior. We can look at the constant, which is 10, that gives us the y-intercept. Okay. Factored form also gives us information about what the graph looks like, but it gives us different information. And specifically, we can tell from factored form what the x-intercepts are going to be. Now, what I want to remind you of is that the x-intercepts are when y equals 0, because everywhere along the x-axis, you are at a height of 0. So for this particular example, if I wanted to figure out the x-intercepts, I would have 0 equals x minus 5 times x minus 2. We talked about this on the first day. If you're multiplying two things together, in this case two factors, and the answer is 0, one of them must be 0. So we can tell that either this is 0 or this is 0. Okay? If the first one's 0, x minus 5 is 0, that means x is 5, because 5 minus 5 is 0. And if x minus 2 is 0, x is 2. So these are my two x-intercepts. Okay? We can also tell, because the number in front of this is a 1, we can see that the leading coefficient is positive. So from that, we know that this thing is going to start in quadrant 2 and end in quadrant 1. So if we were to do a sketch, then firstly, we know that these are the x-intercepts. So one x-intercept is at 2, and one x-intercept is at 5. Okay? We also know that this starts in quadrant 2 and ends in quadrant 1. So it's going to look like that. Okay? So what can we tell about factored form, we know the x-intercepts, or we can pretty easily figure them out. Okay, so A is our leading coefficient. Okay, this tells me whether this parabola is going to open up or down, or in other words, the end behavior. These two factors tell me about the x-intercepts of the function. And in this case, you would have one at x equals r and one at x equals s, because r minus r is 0 and s minus s is 0. Okay, so here's an example of a question that you could be asked. Okay, explain why the function y equals negative a times x plus r times x minus s, where a, r, and s are different whole numbers, could represent the partial graph below. Okay, now explain. What I want you to do with this word explain is make clear why this equation could represent this graph. You need to create a connection between equation and graph. And what I would do is pick it apart one at a time. This question would probably be worth 3 marks. Okay, so 1 mark for like the negative a part, 1 mark for x plus r, and 1 mark for x minus s. Now, this is also important. A, r, and s are different whole numbers. So just remember, whole numbers are not all integers. It's 0, 1, 2, 3, 4, etc. Right? So it doesn't include negative values. Okay? So when you are picking this apart, what I would do is say the leading coefficient is negative a. Now, why does this make sense? Well, if you look at this graph, the end behavior goes from Q3 to Q4, and that is consistent with a negative leading coefficient. Okay, so that makes sense. Okay, then we also have a factor of x plus r. Okay, if that's a factor, that means that x plus r equals 0 will give us one of our x-intercepts. Now, for this to be true, x has to equal negative r. Okay, so that's also consistent because you can see that on the graph we've got one x-intercept that's negative, one that's positive. We'll get to that one in a second. So this is our negative r x-intercept. So this connects to the negative x-intercept on the graph. Okay, and then we also have a factor of x minus s. Right? Now, that's going to give us our other x-intercept. So x minus s equals 0. X has to equal s. And so this connects to the positive x-intercept on the graph. Okay, so that is one example that could very easily be on an assessment. It would be out of 3 marks, so you would want to, as a rule of thumb, kind of make 3 connections. But the most important thing here is that you have to, at all stages, connect equation to something that you see on the graph. Okay, here's another example. Explain why the function y equals a times x minus r squared, where a and r are different whole numbers, could represent this partial graph below. Okay, now there's something that you need to know about x-intercepts. And that is that you can have a single x-intercept or something called a double x-intercept. And what we have here is a double x-intercept, because essentially in this function, x minus r squared means that we're multiplying that factor of x minus r by itself. Okay? Now, that means we have kind of like two x-intercepts that are the same. That's called a double zero, or a double x-intercept. And when you have a double x-intercept, what happens is that the graph will touch the x-axis and then bounce right back up. It won't actually pass through. So this is called a double x-intercept. Okay? And the graph touches the x-axis, but doesn't cross it. Okay? And that's consistent with the equation. So what we would have here, again, A and R are whole numbers, so they must be positive, is that the leading coefficient is A, which is positive. Okay? That is consistent with the end behavior, which goes from quadrant 2 to quadrant 1. Okay? And then we also can see that there is a double positive x-intercept. That's consistent with these two factors of x minus r squared. So x minus r squared tells us about our x-intercept. So we have to have that x minus r equals 0, which means x equals r. But because it's x minus r squared, it's a double x-intercept. And that's what we see on the graph. Which is positive. And we can see that this must be positive because it's on the right side of the y-axis. Okay? All right, so we're going to finish off today with an application question, and then we'll pick this up again tomorrow. Okay, so here we go. A soccer ball bounces straight up into the air off the head of a soccer player. The function h of t equals negative 16t squared plus 40t plus 6, where h of t represents the height of the ball in feet after t seconds. Okay. First question, how tall was the player whose head hit the ball, assuming the player was standing on the ground? Justify your answer. Okay, so firstly, before we even get into answering some of these questions, I want you to picture what's going on, right? So there's a soccer player standing on the ground, and the soccer player is going to head the ball, and the ball is going to go like this, okay? And it's going to land on the ground, and then it'll probably bounce back up. But we're probably just interested in the path it takes until it reaches the ground the first time, okay? So in this function, we've got these two variables, h of t, which tells us the height of the ball at any given time, and t, which is time in seconds. Okay? Now, what I'd like to do with this is just graph it on a calculator so that we can basically see what that looks like. I'm actually going to do it on, I think I'll do it this time on the Casio. No, actually, I'll do it on both. I'm going to do it on both. I changed my mind. Okay, so I'm going to clear all of this out the way. I will do this on both, though, in case you have a Casio. Okay, so the first function, or the only function, is negative 16t squared, so x squared. And then it was plus 40t plus 6. Plus 40x plus 6. Okay, now if you go zoom standard, you're not really going to see much, Okay, we want to really see that picture that I drew a few minutes ago of the person, the stick figure heading the ball. So we have to go to our window settings and readjust these. And what's really helpful to think about when you are determining your window settings is, what does the vertical actually represent in the context? It's height, or h of t. And what does this represent? It's time in seconds. Okay, so think about heading a ball. How many feet do you think it would go up in the air when you're heading a ball, right? So be reasonable. That's going to give you your y values. And then for your x values, that's thinking about how long this thing is going to be in the air for. And that's in seconds. So if you've ever played soccer or watched soccer, you can hopefully imagine how long the ball is in the air for. I would say it's less than 10 seconds, maybe even, 8 seconds. I'm going to make my x minimum 0 because that's time, and it starts at time equals 0 when the ball is headed. And then I'm going to make this 8 seconds, okay? The x scale of 1 is fine. For my y min, well, the lowest this ball is ever going to go is 0, okay? The y max, it's going to go higher than 10 feet. It's probably maybe going to go like 50 feet. Okay, and maybe I'll make the y scale 5. And then I'm going to graph this. Oh, that's much better. Okay, so we can see everything that we need to see in here. Okay, now, how tall was the player? Well, when he headed the ball, that should actually be the initial height of the ball, right? The player heads the ball when time is 0. So that is that's basically the y-intercept. And that is, in this case, 6, because it's the constant in the equation, right? So how tall was the player? The player was 6 feet tall. And that's because this is the initial height of the ball. Okay, what was the maximum height the ball reached to the nearest foot? So we're looking for this point here. We can do this graphically using a calculator. And in fact, just to switch things up, I'm going to pull this up on the Casio as well. So I'll go down to graph. I'm just going to make this a little bigger. Normal. Normal. Okay, that's a little better. And I'll make this. Whoops. Where'd that go? There it is. Okay, let's make this bigger too. Okay, so I'm going to clear out whatever I had in there. So I'll hit F2 for delete, yes. And I'm going to enter in negative 16x squared plus 40x, and then plus 6. Enter. And then I can go F6 for draw. And if I have to, yeah, I got to change the window settings here as well. So I'm going to go to window, and I'll make them exactly the same. So 0, 8, I think I said. And then y min was 0. And the y max was 50. Okay. And then I'm going to hit draw again. There we go, that's better. Okay, because I want to remind you guys how you can find these various things on each calculator. Okay, so let's now go back to the TI. We want to find the maximum height. We've done that a few times. So second trace, number 4 for max. And we're going to go to the left. There we go. And to the right. There we go. And it looks like the maximum height, that point is 1.2531. Okay, so the 31 is the maximum height. The 1.25 tells us at what time that happens. So the maximum height is 31 feet. Okay, on the Casio, if that's the calculator that you have, then remember everything is under G-solve. So you're going to go to number 2 for maximum, and it just gives you the point, which is kind of nice. Domain and range within the context of the question. Well, we kind of can see the range because we found that max point. Okay, that max point was at 31. So we know our minimum height is 0, and our maximum height is 31. Okay, so we can actually fill out the range right now. So the range is 0 less than or equal to the height, h of t, which is less than or equal to 31 feet. Okay, for our domain is essentially when is this thing in the air? So it starts here at 0, and then it stops when it hits the ground. We need to find that value. Okay, we want to know what that is, and that is the x-intercept. So on a TI, that x-intercept is called the 0. Okay, now the problem, if I start to do this now and go number 2, it's going to ask me for a left bound and a right bound. So I can go to the left, but the right bound is actually out of my window. So when you're doing this, you got to go back to the window settings and actually make a little bit of negative values be seen for the y. So I'm going to make my y min like maybe -5. And although that's not actually part of the function, part of the range, it will allow me using the calculator to find that value, that x-intercept. So now I'm going to go second, trace, and then number 2. And I'm going to go to the left. Left is on this side because here's the 0 here, so here's the left. I'm going to hit enter, and then I'm going to go to the right. There we go, enter, and guess, yes. So that is about 2.64 seconds. Okay, so this happens at 2.640, and so essentially the time values that make sense in this context are anywhere from 0 seconds to 2.64 seconds. Whoops, 0 is less than or equal to time, which is less than or equal to 2.64. Okay, on the Casio, if you want to know that value, you can go gsolve again, and this time you're looking for root. Okay, and there it is, 2.640. Okay? All right. So that is the end of the lesson for today. I would like you for homework to do questions 1 to 5 on pages 15 and 16. And if you need to see the answers, if you want to check your answers, please go on to the completed notes on D2L, and you guys can check your work there. And I will see you tomorrow.